So in addition to this, we have the waveform side. So we also have the channel model side of things. These are implemented according to what's called 38901 from 3GPP. There are 3 different channel models at this point. There's a tap delay line channel model, cluster delay line channel model, and high-speed train as well. They are slightly different. This is like a 3-dimensional channel model that deals with clusters. This is a more statistical tap delay line model, and they have various profiles, which are something like indoor, outdoor, with the office environment, they're different profiles. And these channel models are implemented from measurements in 3GPP standard. So we didn't come up with these, they came from 3GPP standard. In addition to this, something that's a lot of interest in the last few years is actually ray tracing. And we have an implementation of ray tracing channel model with what's called shooting and bouncing rays. What this allows you to do is basically get you can see the multipath from the reflections, and you can also get basically the signal strength, and you can get the impulse response of the channel that way at each receive point. And this can be leveraged inside of what's called a site viewer, which allows you to import map data. So you have buildings here, so you can place the base station on the building or on the ground or wherever you need, and you can place various sites at the receive and run the ray tracing, and that can help inform things like beamforming. As you can see, you can also visualize beamforming. You can look at interference mitigation kind of beamforming techniques based on that. So it's a very useful tool to start looking at real kind of scenarios. So in this case, the previous models were all kind of statistic models. So the distance between the base station and the UE doesn't really impact. It doesn't matter if your UE is next to you or far away from you, you still get the response is kind of the same. But here, of course, distance does play a part because it's a different type of channel. When we put together the transmitter, which was the waveform generation components, and the channel model and the receiver, we put the channel model in the middle, we can get a link level simulation. The receiver simply just undoes all the steps of the transmitter, and we can apply also hybrid arc system to the entire example as well. So if we take a look, go to the end-to-end, you can see that there is throughput simulation for both uplink and downlink, and also a block error rate. It's very detailed example. It has a lot in it, but essentially what happens is you encode a slot with user data. You apply pre-coding. You do OFDM modulation. It goes through the channel, which obviously makes impairment. Then you do synchronization, and then you undo all the steps. OFDM demodulation. You do channel estimation, equalization, and then you decode the user data and compare. And then that drives also a hybrid arc around it. So it's a lot of MATLAB code, but if I were to just open it up and we scroll down, so these should look very similar to these, right? Because it's the same parameters that we apply to the user data that would already be familiar with from generating just plain waveforms. The channel model, this one, the CDL or the TDL, and then it is a for loop to iterate over SNR values. Then there's a second for loop to iterate over the number of slots. In the simulation, I think this is maybe 10 frames, or it's kind of short. And for each slot, then we encode some data. We would add additional symbols like PTRS if needed. We would do OFDM modulation. That goes from a carrier and a grid, which is just a matrix in the frequency domain, to now a time domain waveform of IQ samples. I just look at this. Yeah. And then we pass it through our channel. Stop. Equalization, pre-coding, sorry, estimation. Oh, this is for the PTRS, never mind. And then equalizing our grid after we've recovered it. We get another equalize symbols. And then there are different ways to do things like EVM and so on and so forth. It's quite a long example. Just get rid of these breakpoints. For statistical significance, you want to run this for tens of thousands of frames. Obviously, this is just 2 frames to make it fast and quick to run. What happens is this is enabled by something like using parallel computing. So you can actually farm this on number of workers using par4 if you have parallel computing toolbox. That can also be on a server somewhere with parallel server. So you can set up jobs like that and run them. So that's also all supported. More recently, we've started to add a GPU support for some of these functions in the link in order to enable the acceleration that GPUs will give you when you are doing matrix operations. So that's a kind of a new area that we've added support for. By the way, so this is, I'm talking about 5G Toolbox, but if you were to look at, for example, LTE folder, you will find very much the same structure. You will find throughput, bit error curve examples, various different versions of throughput examples based on various releases, 12, 14, and so on, including things like V2X and NB-IoT and so on. So it's very much follows the same structure of how we simulate throughput. On the signal recovery side of things, there's a couple of different examples there. They are very much geared towards working with also live data, off the air data, real signals. And one of them is the cell search and MIB and SIB recovery, which again, you should be able to see it under the signal recovery and reception. LTE has one too, cell search MIB SIB1 recovery, NB-IoT, cell search MIB and SIB recovery. You can find these. And that can be augmented further to actually do scanning and decoding LTE waveforms live off the air. So you put an antenna down, turn this on, and it'll capture for you and decode what cells are in the area and so on. You can use some very low cost radios for that, even just one of the RTLs or even just a Pluto radio if you're not familiar with it. It's very, very low cost. You can see that this is a lot more complex because we have to do what's called the synchronization procedures. That is looking at the initial primary synchronization signal, secondary, and starting to decode various parts of the waveform. So that's the master information block followed by the system information block 1. Changing gears a little bit. So we talked about the standard compliant waveforms, how you get into an end-to-end link simulation and so on. Something that's really kind of playing into wireless as we know it, like the standard cellular wireless, is actually satellite connectivity in the last few years. So that's become really a big topic. What we now have capabilities to do is we now have a satellite communication toolbox that allows you to do one of many things. One of them is orbit propagation. What we have is you're able to propagate using 3 different algorithms. So one is Keplerian 2 bodies, very simple. Then there is SGP4, and then there's SDP4, which is for deep space. But SGP4 is like the highest sort of fidelity propagator that is there. I'll show you how this works in a second. In addition to that, you can when you propagate, what you can understand is you can see axis analysis when your satellite is overhead and for how long for the simulation. But when you apply transmitters and receivers to your ground station or your satellite, then you start to talk in terms of power. So they will have some receiver sensitivity, they will have transmit power, and then you can start looking at link budget. Like I said, there's interplay here between the transmitter receiver kind of functionality and adding a specific antenna or array onto your transmitter that will take into account the bore side of that, wherever you pointed into the link budget calculation. So you have a lot of freedom to go towards kind of realistic simulations here. And you can start playing around with some tracking algorithms to do some beam steering, especially for electronically steered antennas and so on. A lot of room for using these simulations in many clever ways. You can look at various ground tracks and fields of view for a specific orbit where it actually goes along the Earth, gives you kind of a visual confirmation of what you're doing. In addition, you can look at sky plots. So there's some GNSS applications there as well. So that's the time varying axis that I mentioned. Basically, if you have satellites moving overhead, at what point does your ground station see that satellite and for how long? So you can see when you have access, you can see visually when that is achieved and what is the movement of the satellites above your ground station. The link analysis, like I said, we start talking about power here and free space path loss. When do we actually close a link? This could be a link that is between a multi-hop situation, as you can see here. So it could be one ground station needing to talk to one satellite or via another ground station. So we can get an understanding of when this link is closed and for how long. Calculating the Doppler, this becomes really important in high Doppler environment. If we are looking at something like cellular over satellite, we need to know the Doppler. That's probably our biggest challenge here over, for example, LEO constellation. By the way, you can do LEO, MEO, GEO, whatever, or mix of any constellations in one simulation. We've worked a lot on improving the performance of these simulations. So you're looking at tens of thousands of satellites that you can visualize and propagate, and it's all kind of matrix operated. So everything happens really fast. The visualization part is just replaying it from the memory. You can already compute things without waiting for the simulation to play. So ground station is stationary, but a platform can move. So not just a ground station, we can put a platform on there which has some trajectory. Here is like an aeroplane. We can also apply the STL, like the CAD model, I guess STL file of the moving object. So it could be aeroplane, drone, boat, whatever. And we can apply a custom trajectory to it with various waypoints along the way. And the propagator will close the link and show access at the correct points because it will propagate all the actors at the same time and then compute. So let's take a look at that. If we go back to our doc, and we can look at the satellite communication toolbox. To get started, open one of the get started examples. They can get harder and harder and more complex, but it's a few lines of code and everything is object oriented. So initially we set our date, stop and start time and the kind of granularity, how many seconds we wish to propagate after, like the step size, if you like, and we make a satellite scenario. It is just an object. Satellite scenario has various properties. Satellites that can be added, ground stations, platforms, nothing yet. We've not added anything yet. We can add a satellite. So the satellite can be added by two-line elements or can be added by its orbital elements. So we just imported two-line element file of these two satellites, or we can add via the orbital elements. So we are now just checking what are the orbital elements, but we can also add the satellite using orbital elements. So you can make up constellation yourself that way. These are the orbital elements, and we can query where these satellites are at each point in the simulation. At this time, what is the latitude, longitude, altitude of this satellite? So adding ground stations, we simply provide latitude, longitude. We can add as many as we want to add. We can return something like azimuth, elevation, and angle for the ground station, between the ground station and this satellite for this time. Of course, if we just say, give me the azimuth, elevation, and range from the ground station to this satellite for the entire simulation, we can also do that. My satellites are between the first satellite and the ground station for all of time. We can just do that. So we have 301 steps in our simulation. We very quickly just get all the results in one shot, so we can do that straight away. Then playing, we are just simply playing from memory. So very easy, you just kind of build on top of each other the complexity of the simulation. In addition to that, we also have a link budget app to help you get started with the link budget. Typically, you would do maybe some Excel or some sheets that get passed around people. But if you have the app, you can just open and close and save that link budget session, which gives you also a link availability. Also now a time varying link budget you can look at. So basically it's integrating the the simulation aspect, the full propagation into the link budget as well. And you can do uplink, downlink, crosslink as well. Equations here, custom losses. So you're not limited to these losses that we compute for you. Coverage maps and capacity. So this now is kind of augmenting the capability of the orbit propagator to provide you the signal strength. What happens if you place a ground station at every location on the Earth where you want to have coverage and you compute the signal strength? Well, you kind of discretize, a way to compute the coverage over different areas, depending on where your satellites are. So you can see here, if we take it over Australia, we can build a map, a heat map of our signal strength. This is also useful for things like non-terrestrial networks, where different antennas or different arrays can provide different coverage on the ground. So we can evaluate that as well.